Okay, I'm going to try to go faster through this video, so hopefully we can get through all of it. I changed one thing about the last question that we were talking about so that it makes more sense, and this is going to be how it's going to be in the future. It now says a non-zero net force acts upon an object. And when a non-zero net force is acting upon an object, then it's accelerating. That's an unbalanced force there. Okay, so Newton's first law says that inertia is the tendency of an object to resist a change in motion. If it's holding still, it's going to want to stay holding still. If it's moving forward, it's going to want to keep moving forward in the same direction. And an object with more mass is going to have more inertia. Moose has more inertia than a bird. Newton's second law says that when an object is experiencing unbalanced forces, it's going to accelerate. And this means that the object will either speed up, slow down, or change directions. An object's acceleration has an inverse relationship to its mass, meaning if you are pushing a fridge and a shopping cart with the same amount of force, the fridge is going to move slower, right? Pushing a fridge and a shopping cart with the same amount of force, the thing with more mass is going to have less acceleration. That's an inverse relationship. And acceleration has a direct relationship to the amount of force applied. So if you apply more force, then there's going to be more acceleration. Okay, that's direct versus inverse. Okay, so for this one, F net, the net force, equals mass times acceleration. If there is a non-zero net force, then there's going to be an acceleration, and you can tell how much acceleration there is based on how much mass that object has, and also how much of that net force, how much of an imbalance of forces there are. Okay, when you give your friend a lift on your bike, you have to pedal harder and faster to keep the same speed as you did when you were on the bike alone. I guess this is kind of both. I guess it's more this one. I guess it's more this one now that I think about it. I was thinking that since there's more mass when you add your friend to the bike, then that's inertia because it takes more force to move something that is more massive. So it's kind of both. I'll put it in the middle actually. But you have to pedal harder and faster to keep the same speed. So it's kind of this one too. To keep the same speed. Yeah, I mean, it's kind of both ways. Because if you're more massive, it's going to take more of a net force to accelerate you. But this is talking about the same speed, so it's kind of both. Okay, a smaller cannonball leaves a cannon much faster than a larger, heavier cannonball fired at the same time. So this is kind of like pulling out that mass there. So the more massive the cannonball is, the less acceleration it's going to have if it's leaving from that same cannon, right? So mass has an inverse relationship to acceleration, is kind of what that one is saying. Let's see. You are standing in a subway train. The train suddenly stops, but your body continues to move forward. That is inertia. It is much easier to carry your backpack when it's empty rather than when it's full of books. So same thing with the bike thing here. You can kind of see it both ways. Your backpack has a certain amount of inertia when it is empty and when it's full. And when it's full, it's going to take a lot more force to move it around, just in general, especially if you're trying to change directions or get up or get down or whatever. But also you can see it like this. So again, it's just that kind of like pulling out that mass has a big impact on how much acceleration is going on and how much force it takes to accelerate something. Okay? So a girl is going down a slide. As she reaches the bottom, friction causes her to slow down and stop. So if you want to think about that, that's definitely going to be an unbalanced force. If there's a change in motion, that is an acceleration or a deceleration. So that means that the downward motion is slowly becoming overtaken by the force of friction, which is causing her to slow. Okay, so now we're going to do some system schemas and some force diagrams. Okay, so this one is pretty easy. We've done this a few times now. A book rests on a level table. So the system schema, remember we have our dotted line surrounding the object of focus. So that's the book in this case. And system schemas always include the earth because we have to include the force of gravity that's pulling it down, otherwise things are flying around in space. And then we have the table, and we have the normal force that is supporting the book from the table. So this normal force is the support force. You could also say that there's a normal force between the table and the earth, and that would be fine too. As far as a force diagram, the big ideas here are just that we have gravity pulling the book down, and we have the normal force supporting the book upwards. So here it gets a little bit more complex, and your diagram might look a little bit different than this. When I actually started putting this together, I was like, oh. So you can change this around if you need to. But the sledder is the object of focus, and she is sitting on the sled. She is coasting rightward while slowing down at the bottom of the hill. So there's a normal force from the sled supporting her. There is a normal force between the snow and the sled, again supporting. There is the force of gravity between everything and the earth, and you can always recognize the force of gravity when the things are drawn for you already, because it's a dashed line, and a dashed line shows you that it's a non-contact force, meaning it doesn't have to, like, you can jump up in the air and not be touching anything, and gravity is still going to pull you back down. And then we have the force of friction, which is what is causing her to slow down. Friction between the snow and the sled. So here's what that force diagram looks like. Force of gravity is pulling her down. Normal force is, the support force is pushing her up. And then there's the force of friction. Now she has momentum going this way, but there's no applied force in that direction. Yeah, this is one thing I don't like about force diagrams, is they don't show that there is that, like, she's moving right now in this direction, but this is the thing that is slowing her down. This is the unbalanced force that's acting on her. If we were to do the equation about it, that's what we would see. Okay, so system schema for this one, we are looking at a large crate that is being pushed leftward on the carpet at a constant velocity. So I'm going to go ahead and copy a lot of this real quick. I'm going to change this to crate as the object of focus. This is going to be the carpet. And there's going to be a force of friction there also, so I'm going to draw that real quick. And there's also the force of gravity between the crate and the earth, and also between the carpet and the earth. Okay, so the force diagram here, we have the normal force pushing up, we have gravity pushing down, always a good place to start, and we have being pulled leftward. Okay, so there is an unbalanced force towards the left, and that's why that crate is moving to the left, but there's also certainly the force of friction pulling back. So if there was no friction, this force would do a lot more, but this much of that force is canceling out that movement. So let me just go ahead and label these real quick. With the force of friction, we have the normal force. We have, oops, I put that in the wrong spot. This is the normal force. We have gravity. And we have, so we actually need another circle here. We need something to apply, to do an applied force. So, say person. And, yeah, I'm going to add this line between the crate and the person. And that's going to be an applied force. But do you know what I just saw about this? They keep doing this to us. It has a constant velocity, so it's not actually accelerating. So that means that these two forces, the force of friction and the applied force, are going to be equal. So I'm just going to copy and paste that, and I'm going to flip it horizontally. And that shows that it's not speeding up or slowing down, it's just traveling at that constant rate over the carpet. Okay, so on to the next one. All right, so this is an upward rising elevator that is slowing down. It's not touching the elevator shaft. So it's going up, but it is slowing down, which means that the force that's pulling it up is being overcome by the force of gravity, meaning that the force pulling upward is getting less and less. Let's see. So here it comes. I'm going to draw this. I'll pause myself for a second. Okay, so here's how I drew this one. So we have our elevator, the object of focus. Let me draw a circle around that. Dotted line circle. And that elevator, of course, is connected by gravity to the earth. Let's make this dotted line real quick. And I'm going to send it to back. Oh, not that far back. Sorry. Bloopers. Okay, now you can see it. Okay, so this elevator is, of course, connected to the earth by gravity. It's being pulled down. There's that force pulling it downward. There's also a cable pulling it upward, and that cable is connected to a pulley. And you guys will remember that there's a force of tension when we have any kind of cable, leash, wire, anything like that that can be pulled tight, where you can feel that force. Like, I always think about, like, if you're walking a dog, right? The dog can feel the force on its end of the leash, and you can feel the force on your end of the leash because there's that tension there. That leash is tight. So there's that tension force there, and then there's the applied force that's pulling the elevator upwards. But if we're looking at a force diagram here, then what we can see is that the elevator is slowing down, meaning that the force of gravity is getting stronger and stronger in comparison to the force of tension. So what that really means is that the cable is not pulling as hard on the elevator. And as it pulls less hard, then meaning there's less of a force, meaning there's less acceleration on that same mass, right? So it's all these things you guys have been thinking about, but like kind of like backwards, flipped upside down a little bit, right? Tension is becoming less and less in comparison to the gravitational force, and that's why it's slowing. Okay. This is probably going to be 3 videos. Okay, I figured it would be. Okay, describe how the object is moving. So a horizontal, notice this is a position time graph. We've talked about velocity time graphs and position, but this is position time. So a horizontal line on a position time graph means that the object is not changing position as time is going by. The object is not moving. Okay? A straight diagonal line means that the object is accelerating at a constant, no, it is going at a constant velocity. This is a constant velocity because remember, most of the graphs that we saw for a long time were all straight lines like this, meaning that the thing is traveling at 6 meters per second consistently every second. 6, 12, 18, 24, just like you would expect. A curved line means that there is an acceleration. So meaning that it starts off going 6 meters per second or something like that, and then the next second it goes 8 meters per second, and then it goes 10 meters in that same second, or in the next second, and then the next second it goes 12 meters or 14 meters or something like that. So it is speeding up as time is going by. Position is changing more as time goes by. A gradually sloped line, like D here, means that the velocity is, it's not going very fast. A steep line means that the velocity is quick, it's moving position a lot over time. A gradually sloped line means that it is moving more slowly. A steeply sloped line like E, there you go, means that it's moving quickly. So quickly and less quickly. I'm going to stop this video here. I'm going to show you how I wrote that. So there's my answers. Horizontal line means the object is not moving. No change in position as time is going by. A straight diagonal line means the object is moving at a constant velocity. A curved line means the object is accelerating, covering more meters every second. A gradually sloped line means it's moving pretty slowly. A steeply sloped line means it's moving more quickly.